Okay, welcome to the Satellite Application Virtual Training for Students organized by the AMS Satellite Meteorology, Oceanography, and Climatology Committee called the SATMAC Committee. The goal of these training sessions are designed as an opportunity for our students during either the summer or winter breaks to learn new and interesting satellite applications enabled by research activities and new satellite data products conducted by NOAA, federal and university labs. My name is Wang. I'm one of the committee members that are organizing those sessions. And in terms of work, I work here in the University of here as a professor. And there are many other members that in the committee helped on the sessions, and I will put their names in the chat. In the last year, when we started this series of trainings, we had 4 training sessions in the summer of 2021, and we covered topics from satellite data access and the visualization, satellite luminescence of smoke and dust particles, and to satellite luminescence of sea surface temperature and the sea ice. And in this year, 2022, we only planned for 2 sessions in a series focused on the application of the geostationary satellite-based lightning imagery. And yesterday we had a first session, and today we basically have a second session. Yesterday's session focused on the global lightning mapper, the introduction of that. And today's session will focus on the GRM's application and case studies. And we are very happy to have Joseph Patton and Dr. Scott Rudlosky to give us the training and to talk about the applications and the case studies. Joseph Patton is a research scientist with the Cooperative Institute for Satellite Earth Systems at the University of Maryland College Park, focused on the lightning research and training. Scott is a physical scientist with NOAA, and is also the GLM scientist for the satellite mission. So with that introduction, just get time back to Scott and Joe. The floor is yours. Thank you.
Thank you. Yes, and welcome back to those who were able to attend yesterday. As was mentioned, and I described in the first session, we really wanted to provide an overview of the GLM yesterday and where to access some of the imagery. Today, we're going to shift our focus into how the GLM data are being applied. And so it's some similar material will be reshown, but a lot of new stuff today. So I think we already introduced ourselves, but just to be thorough, Joseph Patton is a research scientist at the University of Maryland, previously worked as a forecaster with the National Weather Service in Goodland, Kansas. He really is our point person now with the GLM training, especially with the Weather Service. And I myself work for NOAA NESDIS and serve as the subject matter expert on lightning and also the science lead for the GLM. So this is the course overview for yesterday. That session was recorded, and so you can review that at a later time. Today, we have a longer time, so we're going to make use of the 2 hours today to allow for a little bit more in-depth introduction up front, and then more time for you to work with the imagery and come up with some new ways to view the data. So this view here, this shows the field of view from the combined GOES East and GOES West geostationary lightning mappers. And so you can see the broad coverage over what are some very data sparse regions, especially out here over the oceans. And so within this region, we have continuous lightning observations. And so we get very fine resolution in terms of lightning climatologies. And so what I've shown here, just as an example, I've taken a subset and zoomed in, and you can see how fine the details are here. You can even see some evidence of the rivers here in the Amazon, but especially the mountain ranges. And then a very sharp contrast as you approach the coast here. And so these are the types of observations that scientists are working with to better understand how lightning occurs, and then translate that into the information that users can act upon. So in terms of the seasonal patterns for the GLM, they match what we would expect from the ground-based lightning detection networks that have been around for a couple decades now. And so we see the expected seasonal shift from the northern hemisphere to the southern hemisphere and back. What I've shown in these panels, it's probably hard to see, but this top left one is December, January, and February of 2018 and 2019. And this panel is for the GOES 17 or the GOES West GLM. And this panel is the exact same period of time, December, January, February of 2018, 2019, but for the GOES East satellite. And so the seasons progress in time. So the next 3 months, March, April, May, June, July, August, September, October, November, all the way through till March, April, May 2020. And the reason I'm showing this is one, to show the changing distributions as the seasons progress, but also to show that the data quality has improved quite substantially in time. And so we could probably have an entire 2-hour workshop understanding how these improvements came about and what you still need to worry about in terms of data quality. But I think this slide will suffice to show a lot of the issues that we had early on aren't issues anymore. And we'll work in discussion of some of the other issues as we show you imagery later on. But without getting into details, you look at this panel here versus this panel here, much cleaner. And again, if you look at March, April, May of 2019, just 1 year later, a lot of their solar artifacts are gone, and just a much cleaner distribution. All right, so I'll shift the focus now for the next maybe 15 minutes or so. I'd like to describe the GLM Value Assessment that we conducted last year. And the reason for this, we had a motivation was they're planning for the next generation of geostationary satellites. And during that process, they do an assessment to try to understand what types of instruments and what types of capabilities will be needed for the next generation. And so we went through and we captured societal and forecast benefits that the GLM that can be attributed to the GLM. And we looked at benefits by assessing how the public benefited by decisions that were made by end users. And so we looked and we identified these benefit pools, which I'm going to describe on subsequent slides. And then we described some additional analyses that would be needed to really put dollar values on this. And so it's a very challenging subject to actually attribute value to individual sensors as part of a very complex system. All right, and then finally, as I said, I'll show a few slides on each of these use cases. It's how they're used operationally to influence the decisions. So this next slide here, I went ahead and pulled the summary up front so you can kind of get a feel for what I'm going to show on the next few slides. But with as new as the GLM is, it really was exciting for us to see just how broad of use has already been made of it. And the second bullet on this slide is as important as any. The GLM now provides a national and international baseline of freely available lightning data, and it establishes a baseline for widespread government and industry implementation. And so before this, there was a lot of different networks that detected lightning over with different detection capabilities over different spatial domains. And they were provided in somewhat similar formats, but there was differences. And so now the GLM provides something that can be accessed for free and really will help move these applications forward. There is, as we mentioned yesterday, that there's a change. We're moving from a traditional point source of lightning information to a 2D map, that accurately portrays the full spatial extent. So we show lightning skeletons and just the real intricate nature of these optical observations. We've shown, I will show on the next few slides, that many operational users have embraced this new source of lightning data, and they've already incorporated into their workflow. And so we expect this value to quickly multiply. Despite this, the GLM really still is in its infancy, and much of its value is still waiting to be fully realized. And so you'll see that on the subsequent slides, some ideas for research that's needed to improve things moving forward. All right, so here are the application areas that we split up into. And again, I'll have one slide on each of these. I imagine some of them will be of more interest than others to you. Without going into them here, I guess, and we'll talk a lot more. You saw some of this imagery yesterday. We'll talk about more of it later. So I'll just go ahead and jump right in. One of the main ones here is improving lightning safety. And so I have an animation over here on the right. You'll see a lightning flash that comes overhead, and it'll come to ground once and then travel several more kilometers and come to ground again. And you can see that's a problem because there's a fireworks display, and presumably there's folks out there watching the fireworks. And so it's really important to understand not just where this lightning hit, but where it came from, because anywhere underneath this lightning flash, as you can see, is at risk of being struck. And so the images to the bottom right here, from the traditional ground-based lightning networks, you're going to see these minus signs and these plus signs and maybe some squares for intercloud components. But what the GLM shows is this full footprint. So what you can see is that these flashes are actually connected. Even though there's no radar return between the lightning flashes, the GLM is showing that these storms are indeed talking to one another. And so as I put a premise statement here, the GLM improves public safety across broad segments of society. The socioeconomic benefit will grow as access is gained by users who are traditionally unable to afford the lightning data. And so I mentioned on the previous slide the idea of the data being freely available. Before that, it used to be that you had to pay for the best data sets. And so now a whole new class of folks that need these data have access to them. So I'm talking about emergency managers, event organizers, athletics officials at local school districts, and the general public. And so there's a lot of this information, as you saw yesterday, is out there. There's still work to be done to make sure that each of the folks that could benefit from these data sets has tapped into them and is leveraging them for their application. Going into the GLM, or in the planning for this generation, the GOES-R set of sensors, one of the main, the most highly anticipated applications for the GLM involved tornado and severe thunderstorm warnings. And so we are really pleased to see that indeed it does have that benefit, that positive benefit. And so what we're able to say pretty confidently is that by integrating the GLM into severe weather warning decisions, it helps to promote earlier and easier warning decisions. It helps to better assess the aerial coverage of the hazard. It helps to reduce the false alarms. And all of these things are improved, especially where you have radar outages or in regions of poor radar coverage. And so we'll show some examples about each of these in subsequent slides. But on the bottom here, I've shown just 1 hour apart, which really isn't doing justice to the GLM because it continuously updates. But what I'm showing here is flash extent density, which we introduced yesterday. The warmer colors are the more frequent flashes. And then we have the severe thunderstorm and the tornado warning polygons in yellow and red. And so you can see the close co-location between the lightning bullseyes and the the severe thunderstorms. Another thing that we found interesting up here, this word map is from the National Weather Service in Huntsville, Alabama. They just queried their forecasters in their office, and they asked, in what ways do you use the GLM during convective events? And a lot of the words you see here are ones that you really like to see. The idea that it increases the confidence in issuing the weather warnings. But even if you read some of the smaller words in there, it's good to see that they're recurring across multiple forecasters. Another one that has a really tremendous potential benefit that hasn't been fully exploited yet is the idea of using the GLM to help improve the safety and effectiveness of wildfire response. And so the GLM helps benefit the firefighter community through unique identification of continuing current lightning, and those are the lightning flashes that are most likely to ignite fires. It helps to better characterize pyrocumulonimbus, and it helps to track thunderstorms, especially in areas where you lack robust radar coverage. And so what I've shown in the animation on the bottom right here is a pyrocumulus event from 2020 in California. And what you have here is a fire that's intense enough that it generates its own thunderstorm. And so you see those blue and white squares and dots. Those are the GLM detected lightning flashes during this event. And the reason this is important is as these thunderstorms pulse like this, they cause very erratic shifts in the wind. And so that's obviously very dangerous to firefighters on the ground and also to air assets that are coming in to help suppress the fire. And so it's really important that not only do they observe these when they first occur, but that they also are able to observe them as they evolve to help keep firefighters safe. And then I mentioned the idea of long continuing current. Not every lightning flash makes long continuing current. And from the ground-based networks, the ones that observe a broad area, they don't measure that variable. And so there's work going on now to combine the GLM, which does observe long continuing current, but doesn't have the very fine, 100-meter accuracy that these ground-based networks do, to combine the two to make a product that that wildfire managers can use to help diagnose fires before they grow out of control. Another one that's really at the forefront, and again, I have these ones up front because they're important, but this one really still needs work. It's shown a lot of promise. We've shown that, especially for short-term forecasts of radar reflectivity, the accumulated precip, and the lightning threat, and models that allow convection. And so, without going into the details about which panels which, on the top here, this is if you just assimilate GLM. This is if you assimilate GLM and radar. And the gist of the message here is that you can get comparable results by assimilating just the GLM data as you would with assimilating the radar data. And so when you combine the two, the GLM does show additional value above just the radar and vice versa. And so it suggests that there's a place for both. Now, especially when you get offshore, some of the studies have shown storms that have moved into the Gulf of Mexico. And if you're looking at it just on radar or traditional satellite, it may look like it's continuing to progress offshore. Whereas if you have a more holistic view of it, you can see that it's actually something that's developing and working its way back up towards the Gulf Coast. And so that's we're really looking forward to seeing what comes out of these data assimilation efforts. One that still has a lot of work to do, but has already shown some promise, is improving precipitation estimates. And so the GLM, we talked about a little bit yesterday, has different characteristics that can help you to determine whether the lightning flash is in a leading convective line or whether it's in a anvil or trailing stratiform region. And so by using those GLM characteristics, you can help to the algorithms that are using just pure infrared or microwave satellite observations. By adding this GLM information, you can help them to better define where you have the most intense convection and versus where you have less intense convection. So that's how they go about improving the precip forecast. Another way that isn't directly related here, but the GLM, by providing the rapid temporal updates, helps with trending, and it helps to fill gaps where you might not have as frequent of observations in the other frequency bands. Another one that, especially moving forward, improving climate applications. So before the GLM, mentioned the TRIM lightning imaging sensor had been up there since the late 90s. And they produced a very nice data record going back. But when you talk about climate records, really 30 years is what you're looking for. And so the GLM comes in, and there's a lot of work going on now, and there has been since the beginning of the GLM, to intercompare the lightning imaging sensor and the GLM to get a better feel for how to combine the two and how to make that 30-year data record from satellite lightning observations. And then planning into the next generation, we'll really get a robust look at any potential signals. The one important note is that the WMO has listed lightning as an essential climate variable. And so that goes a long way in terms of helping to justify some of the projects that are being done in the climate applications realm. And then one that I've looked at very closely since then, we published this report a little over a year ago, is the value that the GLM can provide in filling data gaps. And so the broad spatial coverage and rapid temporal updates help to complement radar over CONUS, and it helps the better, it supports the forecast warning decisions. And so there's, not only over CONUS, where this plot here, this is it's from Cho and Kurdzo, and what they're doing is a fraction of vertical volume observed. And basically where you see the dark reds is where you have the best radar coverage, and where you see the lighter colors is where you have poorer radar coverage. And so the GLM really helps to plug some of these gaps. I mentioned earlier, forecasters are using the GLM to get a better feel for the spatial extent of the hazard. And a lot of that is because oftentimes these storms traverse regions that don't have great radar coverage. And so in that gray area where they're passing off from one radar to the next, there used to be less confidence in whether a warning should be continued or issued or drawn in that area. And the GLM, by providing a continuous set of observations, really helps to seamlessly pass from one radar to the next. And so that's just over CONUS. Where you don't have radars out over the oceans, the GLM is even more valuable because there isn't the alternative. And so that's what we mean when we describe filling radar gaps. And then also one where you lose radars. I have the pictures down there of radars going offline. Hurricane Maria was a devastating storm, and in the aftermath, they were left with lots of challenges. And one of the main ones was trying to keep an eye on the weather. And they had their radar down, and other communications networks were interrupted. And so they made heavy use of the GOES, ABI, and GLM during that period. All right, and another one, I think is the second to last one that I'll describe before we get into the meat of our discussion today. That really, in terms of helping to mitigate aviation hazards, you can think of it twofold. The GLM helps better characterize the lightning risk and increases confidence when you're suspending or continuing ramp operations. And so that helps keep people on the ground loading and unloading the planes, luggage, fuel, people on the jetways, helps keep them safer. And then we also have to think about the broad coverage area and rapid updates and the cost it can provide to the aviation industry through improved diagnosis and avoidance of thunderstorm hazards, especially out over the ocean. So the nose radars on airplanes don't see very far when you're flying at the speeds that they fly. And so if you come upon a thunderstorm that you weren't expecting, you have to divert somewhat suddenly, and it's not efficient. And whereas if you saw that thunderstorm earlier, you could divert and save a lot of fuel and time. And I think something on the order of 10 minutes is the rough order of magnitude that I've seen so far, is that with the GLM, with a tool based on a GLM in the cockpit or access to it in the cockpit, they can divert about 10 minutes earlier. And I don't remember the exact numbers. We have it in our report of how much that translates to in fuel costs and time savings. And this plot up here, I don't know, we're going to make all these slides available to you afterwards. So I definitely recommend you zoom in on this one and click on HD down here on the bottom. But what it is, this is from Lockheed Martin. The backgrounds are what basically is what the GLM's detecting lightning from. Those are the background images. And then over top of that, shaded, are the actual lightning flashes. And you can see these flashes up here. And I don't know if you can see it, but there's little red dots in here. If I zoom forward in time, once it's dark, now you can see a lot more of those red dots. See if it'll let me go. No, unavailable. That caused trouble. But what you can see is these planes trying to shoot the gap. They're flying in between all these different thunderstorms here. Sometimes you'll see them circle until the storms pass and then come in for a landing. But it's mesmerizing to sit here and watch this. And you got to think it happens every day. There's this dance going on in the airways and between the different hubs. And up here, what you see is a lot of these planes are flying through lightning. You know, the lightning is going presumably underneath them. These are some stratiform or anvil type flashes, and they're flying up above them. So it's probably a pretty show, but I don't imagine the pilots, if they knew they were there, they might not necessarily go through there. Sometimes they don't have a choice. They're on a flight corridor and they can't redirect unless it's a certain intensity. So anyhow, yeah, that's the aviation hazards. We were going to show more on that today, but we decided to focus the bulk of our time on tropical cyclone diagnosis and warning. And so I have one slide here that I'll show you from Hurricane Dorian. And there was I saw one of the first questions that came across the chat yesterday was, speaks to it right here. It should be an answer to that question. The GLM clearly conveys convective patterns below cloud top in tropical cyclones, so it helps to better diagnose the TC structure and evolution. And so that aids forecasts of both intensity change, or it mainly aids forecasts of tropical intensity change. And so the main applications so far have been trying to flag potential periods of rapid intensification. So there's been a lot of mixed signals over, say, the last 15 or so years, folks looking with different radar network or different lightning detection networks, whether lightning in the eyewall versus in the rain bands and the ratio had a bearing on what the storm was going to do. And there's been strong arguments both ways in the published literature. And really, I don't know that it's been settled yet. But what you'll see most is folks talking about the eyewall now and relating what the lightning is doing in the eyewall to changes in the larger structure of the storm. And so the introduction of shear, other types of things. So what we're showing here, this is a time series created by Stephanie Stevenson at the Hurricane Center. And this is prolonged eyewall lightning. We'll show a zoomed in plot over here. But you're seeing lightning within 100 kilometers in blue, 200 in that magenta, green is 300 kilometers, and then the intensity is here. And here's the rapid intensification, 30 knots in 12 hours, 30 knots in 24 hours is the definition. And so that's really impressive intensification, unfortunately, right before it hit the Bahamas. So here's an animation showing what the lightning was doing as it traversed the Bahamas. Nearly continuous. One thing you might notice when you look at the tropical cyclones is you'll get a stadium effect, especially at night, where lightning in the eyewall will actually illuminate sea spray or low-level clouds. And by doing that, it actually makes it look like there's lightning in the middle of the hurricane where it should be a clear eyewall. So sometimes you'll see that. There's just another example from a different time of just how intense the lightning was. All right, so now we're going to move on. Joseph is going to present the Hurricane Ida case study. I guess maybe I should pause and ask if anybody has questions about the stuff that I presented so far. We'd love to hear any questions you might have. And feel free to use the chat box too, if you'd like to input questions there. I didn't point you over to Slido yet. We could do that. Maybe once Joseph starts talking, I'll paste the Slido link into the chat box and I'll go take a look at it and see which questions we have active right now. I think the next question, maybe Dyla, if you're looking at the Slido, the next question I wanted to make active is, which of these applications do you think is most beneficial? And so if any of the students or any of the participants on here could go over to Slido, I guess somebody will have to paste that link in there. I have too many screens, I'm confusing myself here, but go over to Slido and let us know which of those applications either you're most interested in or that you think has the most potential value to society. Just kind of interested after those brief one slides, if any of them rose to the top in terms of the impression that was left. So, all right, Joseph, I'll turn it over to you now.
Thank you, Scott. And just to let everybody know, I just put the Slido link in the chat box. So go there and post any questions and respond to the open question for this portion of the short course. So Scott did a wonderful job talking about the lightning through the life cycle of Hurricane Dorian, and especially during rapid intensification. And now we're going to let you all as participants explore a different case study with Hurricane Ida. So before we jump in, I want to give you a broad overview of the tropical cyclone. So Hurricane Ida occurred in 2021, and it formed around August 26th and dissipated around September 4th. And the image here on the right-hand side shows the track as it formed just north of the South American continent, and then moved into the Gulf of Mexico, made landfall, and then eventually shifted eastwards over the mid-Atlantic and then dissipated in the Canadian Maritimes. So potential tropical cyclone development was identified as early as August 23rd by the National Hurricane Center. And this storm was particularly well forecast to move straight up into the Gulf, where unfortunately it caused widespread devastation during landfall, which happened around 17Z on the 29th, with sustained winds up to 150 miles per hour. So hundreds of thousands of people were without power. And there were also tornadoes observed especially in the outer bands of the storm, as is common with landfall and tropical cyclones. And there was also an extensive amount of inland flooding, particularly while extratropical transition was occurring over the mid-Atlantic region. Some historic and deadly flash flooding was observed, particularly for the New York City region. Some of you may remember some of the incredible images of the flooded subway system that was caused by the I think still technically a tropical cyclone at that point, but it was undergoing extratropical transition to become a mid-latitude cyclone, but it was caused by the remnants from Hurricane Ida. So next slide, please. So to help you sort of organize your thoughts as we approach this case study, we have divided the life cycle of Hurricane Ida into 4 stages. So the first stage is going to be the initial tropical cyclone formation when it's just developing out in the Caribbean. So, and that's essentially from 12Z on the 26th to 0Z on the 28th. Then there's a period of rapid intensification and strengthening that occurs just prior, in the day or so prior to landfall. So from 0Z on the 28th to 0Z on the 29th. And then this third stage is from landfall into the initial tornado outbreak as it makes its way into the Southeast United States from 0Z on the 29th to 0Z on the 1st. And then finally, there's that extratropical transition. So the animation that's playing on the right-hand side, that first part is sort of stage 3, where it's making landfall. You can see there's some tornado warnings, some flash flood warnings going on. And then as the image shifts to the mid-Atlantic, now we're in stage 4, where we have this extratropical transition occurring. We can see some flash flood emergencies, which ended up being very impactful for the region. So that animation kind of gives you that overview of that stage 3, where you've got like the more tropical characteristics. You've got those extreme wind warnings. And then stage 4, we said extratropical transition. We see more of like an inland flooding threat. Also some occasional tornadoes still causing damage. So as you go into exploring this case, we wanted to give you these stages to help organize your thoughts. So if you're already thinking, oh, I want to explore something about rapid intensification, then you know that you should be focusing on that time period from 0Z on the 28th to 0Z on the 29th. And as you explore the images which we're about to share with you, we encourage you to bring in whatever resources you may want, maybe something from the National Hurricane Center or one of the local weather forecast office from the National Weather Service during that time. There's plenty of information you can find. But we're going to provide you with all the imagery you need. So next slide. So first of all, an introduction to what some of that imagery looks like. So this is the ABI geocolor overlaid with flash extent density from the GLM. And we can see a Hurricane Ida right now in the Gulf of Mexico. And there's plenty of lightning activity, especially in the outer rain bands. And then as the storm intensifies prior to landfall, we can see some lightning activity occurring within the Eyewall as well. That lightning activity continues as the storm is making landfall and progresses over land. So this is just something to help direct your eye towards what images or or lightning characteristics you may find interesting from Hurricane Ida. And we'll let this finish. Okay, so now we have two sort of meso perspectives. So we'll play the one on the left first. So this is the GOES ABI sandwich. So it's kind of a mix of visible and IR. And we can see the storm forms a well-defined eye just before landfall in Southeast Louisiana. It loses its eye characteristics, but we can still see some intense convection happening in the outer rain bands, where a lot of those isolated tornadoes were occurring. And then we see that convection flare up again, more along a frontal boundary. So we get some baroclinic processes happening, and that led to the flash flooding in the New York City area. So let's play the one on the right. Yep. And we see a similar perspective, but this is the geocolor with FED like we saw in the previous slide. And this is really during stage one, where we've got that initial development. Now we're moving into the Gulf of Mexico. So this is stage two, where we've got, it's forming an eye. It's becoming a lot more mature as a tropical cyclone, a lot stronger wind speeds. And then we get into stage three as it's making landfall. You can see that there's a lot of lightning activity happening in the outer rain bands, which may key forecasters into, say, the potential for a tornado happening in one of those outer rain band storms. And then we get into, we're getting into stage four here, where the extratropical transition is occurring. The lightning activity is muted for a while, but then it flares back to life, especially over that New York City region, as the convection intensifies and drops quite a bit of rainfall. Next slide. Okay, so here is the meat of what we're going to be giving you all to work with for this case study. So in this Google Drive folder, which I will put in the chat, copy and paste. Okay, so that Google Drive link, which is on the slide right now, I just put in the chat box. And what you'll see at that link is you will see several folders. And the folders which have days in them, you'll see like 2021 0826, so that's August 28th, August 26th, all the way through September 2nd. So during the life cycle of Hurricane Ida, there was actually a mesoscale sector centered over the storm for almost the entire time. And the images, the animation that's playing on the right-hand side shows an example from one time of what this of what that mesoscale sector imagery looks like. And we've also gone ahead and made imagery from the three main GLM products that we discussed in yesterday's portion of the short course as well, with flash extent density, minimum flash area, and total optical energy. So we actually have total optical energy, minimum flash area, flash extent density, and then we have three GOES ABI products of channel 2, which is visible, channel 9, which is water vapor, and channel 13, which is the clean long wave IR. We have all of those for every minute of the entire storm. So if you're thinking, oh, I want to look at lightning activity during rapid intensification, we already talked about what time periods that would be applicable for. So you go into that day's folder, you'll see the different products you can choose from, and then you'll see all the 1 minute images. So just peruse those folders. In addition, there are two other folders within there. There's one called composites, and that has like the FED and geocolor that we saw on the previous slide, and the sandwich as well. And that's full of a ton of different animations to look at. And then there's another folder called CONUS GLM geocolor, which has days of that different geocolor imagery and FED as well. So we encourage you to look around. There's a sea of imagery to look at. I think in total it's more than 70 gigabytes. So don't get overwhelmed with it, but find something you think might be interesting, and then try to, if you can, try to put together a story of like, oh, the MFA says that these flashes were large or small, and maybe at the same time these flashes were being reported, there was a tornado that was reported in the area. Think like a forecaster. Think like what is this lightning activity trying to tell you, and how can you put that together to better understand how the storm is evolving in the life cycle of Hurricane Ida. So next slide, please. So there are lots of tools you can use to try to put together an animation if you want to do that. And we're not asking you to, download a gigabyte of data or 10 gigabytes and try to animate that. If you want to find 10 or 15 images and just make a small little animation that you think is cool, that's what we want you to do. So there's a couple of really useful online animation imagery tools that you can make GIFs or videos from. EasyGIF is probably the most popular one, and that supports up to 100 megabytes of images. Another online maker is Image Flip, but it's not as versatile as EasyGIF. And then there's also, if you have a Windows or a PC machine, the Photos app is actually really good at creating images or animations or videos. You just have to go to the video editor, and there's no size limit. For iOS and Mac, the QuickTime Player has a similar function. And if you want to, if you're a little bit more tech savvy, if you have a Linux or a Unix machine, you can very easily do an FFmpeg command from the command line to create GIFs or MP4s from the selected images. So again, we encourage you to explore all the files that are available there. Find a few that you think could tell an interesting story, whether it's a few different products at the same time or one product over a period of maybe 20 or 30 minutes. And just find something that you think is really interesting, whether that's lightning activity in the Eyewall during rapid intensification, or maybe lightning from an outer rain band while a tornado was occurring, something like that. Next slide. Yeah, so this leads us into our group exercise. So we want you to pick an aspect of Ida's life cycle to examine more closely. We set out those stages to sort of organize your thoughts better. Stage 1, initial development; stage 2, rapid intensification; stage 3, landfall; and then stage 4, the inland flooding. So at this point, we are going to direct you to divide into groups and start downloading or exploring the images that you want to use for this exercise, and use those to create a brief animation if you would like, and then compose a brief PowerPoint presentation illustrating your findings with the imagery that you have acquired. So when that is done, we will ask you to reconvene to compose your group presentation and share your findings with the rest of the participants. And then we can go into a little bit more detail about what that lightning activity means for different portions of Hurricane Ida's life cycle.
All right, thank you, Joseph. I think I've done this right. So what I've done is I've made 4 groups. So I'm going to open up some breakout rooms. And so I guess we'll use the chat to communicate amongst all of us. But what we'll do is in these individual breakout rooms, if any of them get too heavy, we may ask somebody to move to another one. But I've broken it up into 4 different groups: the initial development, the rapid intensification, the landfall, and the inland flooding. And I haven't assigned anybody to anything, but I believe that you should be able to pick which group you'd like to go into. If we could have Dyla go into the initiation, or the initiation, the early stages. Maybe I can assign Dyla to that, to initial development. And then are you guys able to, is anybody able to choose where you go, or do I have to assign folks?
I think the host can choose, but other than that, it has to be assigned.
Okay, so let's do volunteers then. Well, you're gonna have to pick one. So I'll just go through the list that I have here. Paul, do you have a preference in which group you would be in?
Paul says landfall.
Paul and landfall. All right, and then next is Kyle. Kyle, have a preference? I guess anybody who has a preference, go ahead. Or if, I don't know if you're going through the chat or not. But so it'll be Kyle, Eric, well, maybe not Eric, but Kelvy, Aaron, Owen, Adam, and Mohammed. Yeah, if you have a I think maybe once I sign you to one. Adam wants to be in the final stage. I saw that come up there. The inland flooding, we'll put Adam in there. Landfall, that's funny. I was just gonna say, Aaron, does landfall work for you? Good timing. All right, how about Owen or Kelvy? Do you guys have a preference? Or Eric? That was Kyle. Mohammed. All right, I sent Dyla to the one. Joseph, which one do you want me to send you to?
How about I'll take rapid justification.
Okay, so there's nobody in there yet. So I'm going to put you there, and I'm going to send Kyle there. And then I'm also going to send Mohammed there. All right, and then Owen, I'm going to put you in initial development. And Kelvy, I'm going to put you in inland flooding. And then I guess, who's left with me? Can anybody still hear me?
So this is Bill, but
June, are
I'm
you still there?
mobile here, so I'm in the listen only.
Okay, that sounds good. June, are you there still?
Yes, I'm here. Yeah.
I guess for Sherry and Gary, you could give them host preferences, and then they could bounce around. Maybe
Right.
for Dyla and
okay.
Joseph as well.
Sherry,
And then
who
I see.
else want to do the co-host? Sherry, yeah.
Yeah. Put Sherry so that she can bounce around, and then Scott Lindstrom.
Scott. Okay, sorry. Yeah.
Do we have all the students assigned now? I see one.
I think so. The only 4 unassigned are Gary, Sherry, Bill, and Scott.
Okay.
Okay. Good.
All right, and Bill Schoberg, I'll send you, just so you have somebody to listen to, I'll send you to rapid intensification, because I'm sure Joseph will be talking there.
That would be great. Thanks.
Yep. All right, and then Gary and Sherry and Scott, I guess we'll just bounce around. I'm going to go check on, doesn't look like anybody else is with Dyla and Owen. I'm going to go see how they're doing.
Okay, that sounds good,
Or
Scott.
landfall. I'm gonna check out landfall. See how oh, there goes Scott. Cool.
Hi, Kyle. Are you there? Kyle, can you hear me? Kyle, which session do you want to join? You're muted, Kyle. Gary, you're back.
This meeting is being recorded.
All right, Scott, can you call meeting to close, or do you want me to help?
Yeah, so I have everybody's coming back.
Okay,
to this
you
main
can do
room.
that. You can do that after your end, right?
Yep.
Okay, good.
Yeah, I think I called everybody back here, so we'll just keep an eye out and see
Yeah, I have a
who
meeting with
the
our,
real troopers are that made it all the way back.
yeah, I have a meeting at your time, 3 o'clock. So I just want to, yeah.
Yeah, we'll
yeah,
be sure to be done by then.
yeah. Thanks. Yeah.
All right, so I think everybody's coming back. I guess if you want to take a couple minute break, if you need to run down the hall for anything, give it like maybe 1 or 2 more minutes, and then we'll come back and kind of wrap everything up. Right. So I think everybody should be back from their rooms. Like I see.
Okay, I'm back, by the way.
All right, Paul's back. All right, so Paul and Aaron sent a slide that they put together, presentation, or some animations from landfall, the flash extent density product over top of the visible. I joined each of the rooms and kind of talked about some anecdotes. Does anybody from one of the rooms other than the one I just mentioned want to describe what they looked at? Anything they found interesting? And don't be shy, there's not too many of us here. I guess we could end the recording for this session, this part of the session, June, if you don't mind. I think we're all done with the recording aspect. Or I guess I can do that too.